So we talked about the idea that there's this idea of an independent variable and a dependent variable in designs where we're looking for relationships, so association or causal claims. Now, I prefer to leave the phrase independent and dependent variable to the context of experiments alone, because an independent variable is supposed to be by definition manipulated, which is only done in experiments. So that means there's a bunch of kind of near synonyms. So for example, the term predictor or explanatory variable, those are near synonyms for an independent variable, which is what you would say if you were talking about an experiment, right? So a predictor or an explanatory variable is basically the input. So it's the thing over here that we say leads to the thing on the other side, the y. So the dependent variable is the y in an experiment, but synonyms are outcome or criterion. And that means it's the output, it's the thing being predicted, right? So the prediction, the predictor, the predicted, right? So if you want to say IVDV, right, independent, dependent variable, I'm fine with that, but just know, like, I might use these other terms because specifically those terms apply to experiments and not everything is. Now, a big problem we have is this idea of the confounding third variable. And this is the thing that only an experiment deals with well. It is very hard to eliminate confounds, which is really the goal in research when you're trying to make a causal claim, is you're trying to eliminate confounds. Now, again, doing this, super difficult. So how is it that we knock this guy out? And an experiment allows us to do that by manipulating the independent variable and controlling for other factors, situational or personal. So great examples. A study identified that as the number of churches in areas increased, the amount of crime in those areas increased. So then the question becomes, well, do more churches cause crime to proliferate? Now, this study was longitudinal, so it observed that the churches were built first and the crime came later, because a bunch of people want to go, well, I bet the churches came to help, right? So the crime was there, churches came, and that's why they go together. Okay, well, that's called reverse causality, and that can happen in some cases. In this case, where you have a longitudinal assessment, that's less likely because you establish temporal precedence, right? So not only are they related, right, step one, but there seems to be an order, churches, then crime. Okay, so that's two of the causal criteria. So can we say that churches, increasing numbers of churches, lead to increased amount of crime? And I hope you probably guessed at it here. The answer is no, right? And why? Because it's not an experiment. To do an experiment like that, you'd have to randomly assign places to have certain numbers of churches and not allow them to have other churches added or taken away. They must maintain a certain number of churches, and you must control for other things. And then you have to observe whether or not crime is affected by the number of churches. Notice, it's just completely impractical. There are so many times that it's impractical or even unethical to do experiments. So for example, does being abused as a child cause adverse outcomes? Well, see, that's when you want to be like, oh yeah, I'm sure that's true, right? Especially if you're a psych student, right? But you can't randomly assign parents to beat their children. That's unethical. So you can't actually do an experiment to evaluate whether or not childhood trauma causes later outcomes to be adverse, right? So for example, increased mental health issues. You can't actually establish that. Now there's other studies people try to put together to get at whether or not that causal argument might be at least somewhat tenable. We don't have time to go into all of these, right? Prospective cohort designs, right? All kinds of stuff. But the whole point is that pure experiment is the way to get there. And there's a bunch of times we simply can't do that. We can't tell places that you must have this number of churches. We can't tell parents that you must or must not, right, beat your child and you have to adhere. We can't do those things. So experiments would be great, and they're just not always possible, right? So in the case of churches, there's a major confound, population size or density. Right? And it turns out that population density is a confound here. And once you consider that that third variable is what causes both churches and crime to increase, there's no longer even a relationship between churches and crime. So that's a great example of the importance here to think about design, right, to try to get at whether or not your causal argument could potentially be supported. Just because there's a correlation, don't jump to causation. Don't do it. It's really tempting. You'll find yourself wanting to do it all the time, especially when it supports something you already think, like childhood trauma causes increased mental health issues. See, if you just already believe that that's probably true, you just want, yeah, that's totally causal. But if it's something you don't want to believe, like churches cause crime, then you're probably going to resist it. Don't fall in to that confirmation bias, because that's not learning. That's you just thinking you already know everything. The whole idea here is to use data to actually find what is out there, right? So this is super critical. You might think about something, well, what about like smoking and cancer, right? Don't they say smoking causes cancer? Can we randomly assign people to smoke cigarettes? Okay, hey, this is a great one, right? So let's get on this one. The research here started with Dahl and Hill back in the 1950s. And they had this idea that smoking was linked to lung cancer. So they did this first really good study, and then down the road, a bunch of other studies have been done over 70 years. If you actually read labels carefully, what you'll find is that it says smoking may cause cancer. So that caveat is still there, because we can't do this pure experiment in humans. But what have we done? We've done a bunch of really good research across all kinds of populations to get at this. So for example, in humans, they've done longitudinal prospective cohort control trials where you get people and you start measuring them early, and you see some people convert to smokers and some people don't, and you continue to track them and you have them matched for all kinds of other characteristics, and then you see if the people who became smokers, right, do they have more probability of lung cancer. So that's a really good, it's longitudinal, it has controls, it has matching, it's got all these things. So it's about as good as we can do without an experiment. And a lot of epi research, like studying health issues that we can't like randomly assign. So epidemiology, right? And a lot of that stuff, we use these kinds of designs. So we do things like that in humans, right? So we do correlational studies, we do longitudinal studies, we do, cohort control trials, we do control studies, we do all this type of stuff to establish that this relationship is in humans, it's strong, it's replicable, that it's got temporal precedence, that smoking comes before the cancer risk, but we still can't exclude everything else. So what do? Well, we do experiments in other animals. So it turns out one of the earliest studies was that they actually randomly assigned beagles to be forced to be exposed to tobacco smoke or not. And they found that the beagles who were forced to be exposed to tobacco smoke had significantly increased risk of developing cancer. So we could make a causal argument that in beagles, smoking causes cancer, right? But then when you add this to the evidence we see in humans, it becomes very likely that beagles who have similar kind of respiratory systems, right, and they're affected by this. If that's the case, then the causal probably applies in humans. We also do things like take cells from humans and expose them to carcinogens found in tobacco smoke to see whether or not it causes cancerous mutations in cells that belong to humans. So we can do experiments in those types of things. And when we take all this evidence and we stick it together, we can become much more confident that in fact smoking causes increased cancer risk. I'm not saying smoking causes cancer. See, that's not true. In fact, most people who smoke don't get cancer, but way more people who smoke get lung cancer than people who don't smoke. So it significantly increases the risk of developing lung cancer in a very profound way. And that link seems to be causal based on all these lines of evidence. And that's a great principle, that science is about amassing evidence, right? It's not about doing one study. No single study proves anything. But together we get all these different study designs, the continuous finding of relationships. We put it together and we form this kind of strong associations. So in these well-done experiments that support causal arguments, there's always control for factors like situational personal differences. There's randomization to assignments, and then these experiments should be replicated. We should continue to see that this happens, right? And this is exactly the kind of thing we've seen in the smoking and cancer risk literature that has made it stand out so much after 70 plus years of very, very hard work.